So, good afternoon, everyone. Welcome to this special series of lecture by Professor Biman Bagchi. Today is the fourth and the final lecture in this series, which we started on last June, and we had last three lectures recorded and available in the YouTube channel. Those who are joining us for the first time, just to give you a very brief idea of what this platform SMCB is, we are discussing, the statistical mechanics and its applications in chemistry and biology and its allied subjects areas, what statistical mechanics can give us. And to discuss that, we have created this platform which is now more than a year old, and we had very nice back-to-back two conferences and following several talks by many distinguished practitioners and young postdoc and even grad students. So with this brief note, I will ask Professor Bagchi to deliver the last lecture in this lecture series. Sir.
Yeah, thank you, Rajiv. Thank you. So the whole idea was, at one point of time, I found that certain critical and crucial concepts that are more useful than, for example, things that we face in equilibrium stat-mech in dynamics is the linear response and fluctuation dissipation theorem. And we are using that almost everyday life, whether we are calculating by using computer simulations or analytical. But those just don't pervade on the transport properties or liquid state dynamics. They go well into spectroscopy, as we discussed, the relationship in our connection of time correlation function and the experimental observed line shape, Newton scattering or infrared. They are all but time correlation functions. We routinely use that, but we do not know much of the time where these expressions come from. So that was the basic idea, to fill the gap that how does, then when started talking about it, I realized that there are, in order to do that, I have to tell a little bit of the non-equilibrium stat-mech as such, which is a book that I'm writing. And so that started doing the course, but today is the last. I already have talked little, I have taught the time correlation function part. I revised a little bit today again. The main emphasis will be on linear response. And fluctuation dissipation theorem essentially is a consequence of that, and which by itself is more of a concept, can be understood in terms of Einstein's theory or position order technique or Langevin equation. But linear response is the crux of the matter, and it is so important, and that you can see in the book of physicists, physics books, that there's a huge amount of emphasis. They do a lot of Cramer's relations and all those things. And now, unfortunately, in physical chemistry approach, we do not have an non-equilibrium stat-mech book. Zwanzig wrote one beautiful book. So did Van Kampen, but they were not, somehow Van Kampen has nothing to do with spectroscopy. And Zwanzig also has very little to do with spectroscopy. And that kind of not the approach I'll take. Yeah. Okay, so now to this, so a little bit more of a history, then go back, and how does non-equilibrium stat-mech started? What led to the linear response theory? How did it come? So then, so I identified these two. One is the kinetic theory of gas, and this is hydrodynamics. And I said, okay, these are the two things we know in some form or other. Hydrodynamics actually, you know even from high school, class 11 and 12, certain amount of hydrodynamics is done these days. though they don't tell it as such, but we did have hydrostatics and all these things even in late 60s and 70s. Now, but however, what is really not helping the students is to take a synthetic view. That is, if you take a synthetic view where you know how the pieces are written to each other, the pieces are related to each other, how they fit together. I was reading today or yesterday one of Rabindranath's famous lecture in 1930 on delete. After delete, he gave this series of lectures in Oxford. And man, he wrote so beautifully that is even now so difficult to understand what he tried to say. But what he tried to say, one fabulous thing, is that after the dance of the atom induced, and then atoms and molecules in the form of the cell and all these things, then at the level of cell, how I cannot just tell these beautiful words. This is the certain meaningful things won over inanimate things. You read that lecture or just beautiful. But there he said that he used the term cooperativity. He said how different parts cooperatively interact and win over the disruptive forces. Of course, he was an eternal optimist, and that's. But he took so long ago a really beautiful synthetic view of the whole thing. So I think the subject really gains if you have different pieces. You know. So here two main pieces are kinetic theory of gas and hydrodynamics. Kinetic theory of gas give you the transport properties. You know that in your undergraduate. They give you viscosity, then thermal conductivity in terms of mean free path. They also give you equation of state and the pressure, PV RT and PV, P equal to 131 C square. Hydrodynamics, on the other hand, not that microscopic. It doesn't talk of atoms and molecules. It talks in terms of kind of a pre-averaged, local pre-averaged quantities, which are called density. Certain coarse graining has gone in. Local equilibrium, we assume, and that is that I discussed, and that leads to allow thermodynamics. But the important difference between the way we learn kinetic theory of gases and the hydrodynamics goes into giving you time correlation function very quickly, because there is a time correlation function which gives you the Rayleigh-Milland spectra. That's the density correlation function. It also gives you an expression, relation of the current in terms of viscosity. It doesn't calculate viscosity. Viscosity is calculated by kinetic theory of gases. Okay. Now, kinetic theory of gases extended by, we discussed Boltzmann H theorem, how beginning of linear response and many things that Boltzmann did, and Stokes extended it. And then on the other hand, it was very parallelly was growing. Hydrodynamics was extended to smaller length scale actually by Dijan, but then much more was done by Cohen and Dissipation, who got wave number dependent eigenstates. They could generalize to Stokes hydrodynamics to small length scale, finite wave number. That starts at k equal to 0. The forms we know goes over smoothly to Dijan's thing. This is just beautiful. That what happened in the hydrodynamics. Similarly, kinetic theory of gases was being extended by taking binary collision, many particle collision, ring collision. Then they started seeing there are a lot of things, because in kinetic theory, I don't have the Hilbert's name. Hilbert's solution of kinetic theory of gases uses the collision invariants, which are nothing but our 5 Poisson variables. Now, so this was the kind of thing that I will not do too much of phrenology, though I think it's probably done separately will probably help better. So hydrodynamics is that one I said. Other fundamental approaches, I did the kinetic theory of gases in the fundamental approach. because that started the atoms and molecules and direct collision and all those things. What beautifully happened, they're just way developed, but then they were at once they are finite wave number, then they found that the finite wave number extension essentially very similar to what one finds in extended kinetic theory. And then they realized that these two to be connected, there's a bootstrapping required because the time correlation functions given by hydrodynamics can be used to calculate the transport properties given by kinetic theory of gases. These two have to be connected. That's a bootstrapping. That bootstrapping and self-consistency leads to mode coupling theory in a formidable theory. Okay. Now, so this is the what Navier-Stokes hydrodynamics does, and these are the eigenvalues dt cube square, gamma cube square, and these are the ones which then become wave number dependent. And these I already discussed that what a beautiful thing this is. Yeah, now it's hugely come back and made a return. The relative spectrum, many fancy equipments have come. Note that thermal diffusivity with the full width at half maximum or half width at half maximum of divided by q square is the what you call heat mode. Look at the value 10 to the minus 3. Diffusion is remember about 10 to the minus 5. Okay, these are ballpark numbers I've written. So what happens when you go to large wave numbers? So this gives the density fluctuation spectrum that you see gives the density fluctuation, and that goes down to so this low Q part is the hydrodynamics, but see it does not increase, it come down, and we call it narrowing. The heat mode becomes or softening. It actually goes over to the self-diffusion mode. That is what Dijan showed us. I have done it before, but I'm just slowly going to more today's. What we'll do that? What is the linear response theory? I'll come back to a little bit more. Come back and forth, back and forth. That's the way we'll go. That the beginning of linear response theory is the Stokes law. I think I told last time. Stokes law is that if I pull a ball with a string with a force F, then I get a steady state velocity V. So V is the response, velocity is the response, and F is the force. This is Stokes law. This is the first linear response theory that we know. The linear response theory that further developed by Einstein. And we'll derive this from linear response theory in a very quick. So if you do that, does it work? Yes, you do different kinds of simulations. It's amazing. It's really amazing that you get exactly the Stokes law in computer simulations. And remember, Perrin got Nobel Prize of this by doing these experiments with colloids or proteins. I don't know. Important thing is that the friction that you get here is exactly the friction that you get. Now we calculate diffusion because you are doing a simulation, both MD and Langevin dynamics. Langevin is a little more stable because you have noise term. But when you add that, whatever you do, then you calculate mean square displacement, you get the diffusion, and you use Einstein relation to get the friction. You find those two are exactly the same. That means that's why Einstein relation also is sometimes called with the mobility is the fast fluctuation distribution theorem. The reason they call it fast fluctuation distribution theorem and the connection essentially linear response is this here for you to see. This is the origin of that. That's the origin of much of our time dependent stat bank. Okay. So what we will derive such in terms of molecular theories? What we will do, we'll look over linear response theory, we'll do on reciprocal relations, which I told, but I could not do it before because you need the derivation that you do these days, not the long derivation is essentially the derivation was given by Landau-Lipschitz, and that is time correlation. Okay. Actually, in many cases, one such thing I've derived, but this one I have not gone back and looked very much. Okay. So to go ahead, we have to go to phase space. We have to think of trajectories. We have to think of Liouville equation and conservation of phase space is this d rho dt 0, which gives you the Liouville equation, which is given here in the bold in the middle. And this is a huge amount of applicability. Then Liouville equation was transformed into Vijay hierarchy, and to go into that went into the YBG equation and all different integral equation theories essentially originated from here in equilibrium stat mech. These are very, that's why I said the synthetic view is very helpful because you understand much better. Okay, so Liouville equation is derived from Hamilton's equation, and Hamilton's equation here dq dt dp dt. That's nothing but Newton's equation, but in terms of Hamiltonian as an advantage, because you over Newton's equation in analytical work, because the conservation of energy can be put in, which you cannot put in, which is here it is done in put in the beginning. Well, Newton's equation, you put it at the end, you check it that it works out. Okay, so this is a so IL is the Liouville operator. I am a little bit confused here in this plane that I use like this, but I have my students who seems to always put a minus sign from somewhere, and once it just removed I altogether. Okay, so this is the Liouville equation, and this is this formal solution of the Liouville equation, which is very helpful in all analytical work. So the phase space, how do we study the phase space trajectory? There is some one-dimensional linear zones phase space trajectory. Phase space, remember, is space spanned by momentum and coordinate. And in an ergodic system, just to fill it up. And here it is phase space trajectory in 3 dimension, 3 different particles. And locally, they all fill up the phase space. Okay. So as I remarked, what is partition function equilibrium statistical mechanics is time correlation functions, not equilibrium stat mech. They are both based on phase space, and in TCF, because of Gibbs contribution, ensemble picture, we don't have to go through dynamics, we directly go to ensemble average, which then leads to partition function. These I have discussed again and again, and these I have also discussed that. Okay, so now continue. Sorry. So now this is one thing I want to do a little bit. I hope the current doesn't go again. The properties use the self-adjoint property of Liouville equation. This is very important property. One is time translation, which just means along the trajectory if you go, it does not matter. Only the matter is the difference between them. Other is time reversal symmetry. This is also called parity, that t and minus t are in a way it is similar to time translation, but it is given a new property. These two will be using today. Now, I already talked a little bit about density time correlation function. These are very important properties in all calculations and should be calculated. People do molecular dynamic simulation, but we never do the case space. It's very interesting. It's probably difficult because you have to use k as a vector. Okay, so the length scale, what we talk of length scale density fluctuation, we take a small region, consider a sphere, and the sphere is then diameter L, then the length scale that we are probing is the 2 pi by L. So that's why in neutron light scattering that L is very large, but in neutron scattering the L is small, of the order of molecular diameter. So wave number you are probing is 2 pi by sigma, but that is 1 angstrom or so, or a little bit more than that. But in light scattering, that is 0.000 10 to the minus 4 or so, because length is very large. Okay. How do we think of fluctuations? This is very important to understand that much of what we do in statistical mechanics, in biology, everywhere is the fluctuations. So these fluctuations is cost energy. But how do you understand which fluctuations are doing what? And that is then what is the fluctuation? What is the quality of fluctuation? Which fluctuations are populated? And what is the length scale, K dependent of fluctuation? What is the frequency dependent of fluctuation? How do we know them? We know them in a very simple way, is the Landau free energy function. That means we take first term on the right hand side at x average, which these are my equations I've written, and I don't know math type, though I know math type, but I don't know how to make it so beautiful as some of my students know. So it's the fluctuation. First term is 0 because it's a minimum, at the average value is the harmonic surface. But is the second term, which is the most important term, is the second term which gives you specific heat, is the second term in time correlation function. Formula goes over to time, and that gives you the spectroscopy. It is a very intimately connected. That's why when Mukhamel did his nonlinear optics, all through he just did the Brownian oscillator theory. He just used Vx as this one, and it displaced exactly this formula. He got away almost everything. He and many other people. Okay. Okay. So now the density correlation depends by force constant. So this second term is the force constant of density fluctuation. It's very important that understand that this is where the many things of linear response are actually in this equation. This is what I was saying, that these things are connected. And they are connected, like in density, this is a specific heat. Okay. And the that part goes to time correlation function. Okay, now, and when you calculate the time correlation function, again, we calculate fluctuations into like dynamic equation in a harmonic potential. Many things are done like that. Many things. Like as all of Mukhamel's work, or the work that done by Fleming and Cho and many other people, are just this kind of theories, what I'm telling you. You know, and except that there are fluctuations, polarizability, and those kind of things. So now, so density fluctuation, dynamic structure. Now you can talk of diffusion. How do we talk of diffusion? How does diffusion? As I told you, Einstein's theory is considered the first fluctuation distribution theorem by Kuku. Why is that? Because if you take particle and you talk at the tact particle's position going, and you talked of the tact particle density, we use n over tact particle and rho for the collective density. This correlation function is the one that Kubo used to get the A, because one can get the force, and then D is the diffusion. And you calculate the correlation function here, and then you calculate the diffusion, and you demand that they are the same. Okay. So these are the kind of things one does. I'm not going to do too much. I talked a little bit about that, but it's a very important thing. The equations are there you can design spelling is not correct. G should be capital. Now this is called actually Smolkowski equation. In this particular case, it's called Smolkowski equation. Is used widely in plasma. Okay. Now, so Smolkowski equation gives you a dynamic structure of FKT. The solution is given here. And note that D by SK, not DQ squared. If it is NQT, FSQT, then it will be, I'll show later that SQ will not be there. So SQ makes it slower because SQ is big. So two way it slows down. One, thermal diffusion becomes cell diffusion with a factor of 2 or order of 2 or 3. Then another factor of 3 comes from the structure factor, which add the Q equal to 2 pi by sigma, sharply peaked and have value about 3. Okay. So this is the kind of thing. Now this comes a very, very important thing. Why I'm talking all of these things together, neutron scattering, light scattering, then dynamic structure, self-dynamic structure, everything together I'm putting in one basket. Why? The reason is that at large wave numbers, at small separation, heat mode degenerates into a self-diffusion mode. Because only number conservation is obeyed. I've said it many times to many people and I never get tired of saying that. Because this is one of the best things that come out. Energy and momentum are obeyed only at long length scale. This is the basic answer of much of what we do in modern non-equilibrium stat mech. And this, as I said, FSQT. Okay, now what will be next to the important correlation is the current and time correlation function. I'm not going to go detail into that. Time correlation function, there are two, longitudinal and tensor. Longitudinal is easy to understand because remember, if you do the conservation equation, the continuity theorem, then dg dt, G is the current, momentum current, momentum density, dg dt equal to minus right hand side minus grad d dot dt equal to minus grad G. That's a conservation of number. If you take the Fourier transform of that, you get k dot G. K dot G, G is the current, is the longitudinal. So longitudinal current is same as the dynamic structure. So you don't have to do it. Transverse current is the one that is orthogonal to K. And that follows from Navier-Stokes equation that it is given by, the current correlation function is given by the viscosity. So transverse current correlation function is very important thing that we use e to the power minus eta q squared t. It's very important to do transverse current because, see, it's very easy to understand.
if you consider two layers moving relative different velocity relative to each other, maybe in the opposite direction as could be in Kuwait flow or just sliding, then there's a momentum relaxation that gives to dissipation, and that is viscosity. But this is because the velocity in the transverse direction is different. That's why transverse current is the one that is connected to viscosity as comes directly from the Stokes equation. These are very, very important thing, and transverse current plays a very important role in giving rise to is one important contributor to self-diffusion. Actually, the Stokes-Einstein relation, the viscosity is follows from the transverse current. You know, it does not have the self-dynamic structure factor, dynamic structure factor. Mode coupling theory has completely dynamic structure factor. So they do two orthogonal things and get similar results. It was a lot of confusion at one time. Okay, so right now what I'll try to do, I'll quickly go through Kubo's linear response theory, then derive, if it permits, my internet permits, Stokes law. Then I'll derive Kirkwood's formula in a back of the envelope calculation in 2 lines. Then I'll go to position of identity. Now, in order to do that, I now have to open different thing, which is this. So this is the linear response theory. Okay, you can see this now.
No, sir. We still see the PowerPoint only.
Okay. Oh, so I did not share the screen.
No.
No. After before I was sharing the screen. Okay. So let me see that now. Go back. Share screen. Share screen. Now you can see that.
Yeah.
Okay.
Yes.
Okay. So quickly I go through these are one of the main things that I try to teach you and tell you. And this is the linear response theory. This is beautiful stuff. This is Kubo. And let me, it's a PDF, so you should be able to that, and this will be, I'll send it. Okay. How do we do that? Now, remember, I told and wrote that is the first order perturbation theory. And first order perturbation theory in quantum mechanics leads you to the Fermi-Golden in dynamics. I'm talking only of dynamics here. Fermi-Golden rule in turn can be transferred into a time position function formulation. That is what Roy Gordon taught us, and I think I talked about it. But right now, I'm going to give you that how the first order perturbation theory is done in time-dependent statistical mechanics, and this is usually not taught in the book, so I'll go a little bit. So I have a Hamiltonian, which is the system Hamiltonian. So just water molecules, an external field, maybe an electric field or a polarization field that is working on that. Now, if I do that, then I go, I define H prime. Actually, I don't have to define H prime, except I have to keep a time dependence in the force. But H prime couples to a property, a mechanical property, like a density, like a polarization. Better to think of polarization. AR is the polarization and F is the electric field. Then that integral, remember PR E naught R, the solvation that gives you the perturbation. When you create it, this is also the basic of solvation dynamics. When you create a charge, suddenly, that's exactly what happens. And the response we get is a perturbed response, but you say it's the response of the liquid. That exactly is the linear response theory. We don't, I guess, say that, or we said one line within linear response theory. But we don't really, everything goes through time correlation function. So we further decomposed in wave number and not necessary to carry the wave number, but frequency we have to carry. But then we have this kind of a H prime is this kind of a term which is e to the power I omega t constant time dependence, but it's essentially for us trivial time dependence term which in front of it. Okay, now is the interesting thing. Now I go and put it back in my Liouville equation. Remember, my Liouville equation is e to the power ddft into ILFT, fast equality. Now I write the Liouville equation in full glory, H naught plus H prime Fn. Then I separate it out. So one is IL naught Fn, of course, H naught commutator, and then minus AFn. So this is equation 1.4 is the first step in my level equation. Then I decompose. This is the first order perturbation theory is coming. I write down by n particle distribution, my phase space distribution. This is the full momentum and position. N particle distribution. That's the beauty of these things. I decompose into two parts. One say, okay, my one is the system part, the one little the zigzag 1D and 3D particle I showed you. That is disturbed now. That phase space distribution is disturbed by delta effect. Then I go and put it back. Just we do quantum mechanics, all the perturbation theory, all these things was essentially people don't know, but it's all done by Schrödinger. That's why you don't hear any name in quantum mechanics. And then I put on the left hand side the right hand side, and I get right hand side, I get 4 terms. Left hand side, I get 2 terms. Now I remember df naught dt equal IL naught F naught is the 0th order level equation. They cancel each other. Then I have left on the left hand side, I have d dt delta Fn left. On the right hand side, last term has 2 terms linear in there. One is delta F, which is linear, and F itself. So that is the nonlinear term. So I neglect that. So I have now 2 terms left. One is IL naught delta Fn and AF naught F. Okay. So this is the equation now after linearization. This is where linearization comes. Then I solve it formally because this is just the an inhomogeneous first order differential equation. So I know that from my if not high school, certainly from BSc 11.8. If you have any problem, then put this equation 11.8 in 11.7, and you see that you have to remember one equation, which is the Feynman used to say integration within the differentiation within the integral sign, and how to do integration when there are limits are time dependent. Feynman has, you must be joking, Mr. Feynman has this very funny, very nice comments on these things. Leibniz rule, okay, which is very standard, used to be JE exam at one time. Okay, so I have 11.8. Now what I do, I have the distribution, I have a solution. It is fairly simple if you analyze it. Well, it is still formal, because I have not given you anything. I have not given you the F naught n. Yes, F naught n, you know it is e to the power minus beta h. Fs, I can give it to you, like what you have given before. So what do I do now? I do, and this is the F naught n, the same as I told you is nothing but a commutator, which is Poisson bracket, and F naught can be shown then by becomes minus beta a dot F naught n, because this I call Biman technique. F naught, you put F naught into e to the power minus beta h, and e to the power minus h, take the derivative, dh naught dpi come out. You get e to the power minus beta h, that's nothing but F naught n. So you take it out on the right side and you get these things. And this thing is nothing but a dot. What is in the Poisson bracket is the definition of a dot according to Hamilton's equation or whatever. Okay, so I'm pretty smoothly placed. Now I calculate what is the observable. My observable is the response of a quantity B. I calculate the change in delta. That is what my response is to perturbation. And I do that drn, dpn, drn, dfn. So then I put my delta fn there, and I do a little bit of maneuvering here. Remember second equation with the full a dot. Then I use the self-adjoint property and bring it inside. And then I have dfs outside. And main thing is that phase space integral drn dpn f naught n. F naught n now, which has survived, is the equilibrium phase space distribution. I now rewrite as Kubodit as minus mu t ds phi bat minus s. Phi bat minus s is called the after effect function. This is nothing but a time duration function. So equation 11.11 is the mother of all equations like we do in time dependent stat math. So what do I see? That phi bat gives the change in property response to an external field. Right hand side of the equation is time correlation function. In the deriving equation, you use the phase space representation of TCF. Now, in many applications, we have. So I go back, they repeat this thing. What have I done? I have started with the Hamiltonian, h equal to h naught, h prime, my perturbation. I say, okay, this is position dependent mechanical variable A, system variable A with fluctuating. My field is connect just in light scattering or anywhere connecting to that. It's a beauty actually. I further simplify a little bit because I know I would like to mostly work with light or neutron. H prime, but for me, H prime T could be a constant. And then I go back, put it in the Liouville equation, and I find 4 terms. And then of the 4 terms, I find the 2 terms, the left term of one and right one cancel. Last term is non-linear, so I'm left with 2 terms. Then I solve it in a formal way. My first order inhomogeneous differential equation or inhomogeneous first order differential equation. Then I go and see a f naught, write down the commutator or Poisson bracket, and I find the minus beta a naught f naught n. Beauty is that f naught n remains, and that remains because f naught n is e to the power minus beta h. This is just amazingly lucky, really lucky. And then you do some passaging here, equation 11.10, and you find the response. See, B has nothing to do with A at this point, and I get this. So the perturbation response B is given by the time correlation function B dot TA. Beta is 1 over KBT. Okay, so this is the crux of the essence of the linear response theory. The important point is the proportionality is given by time correlation function is the linear, or the thermal average is performed in unperturbed system. This is very important. The thermal average that we have involved here is F naught n, and that's unperturbed. So the 2 equations together constitute the central expression Gaussian linear response theory. So then you can do many other, kind of thing. Go to page, make delta V position dependent, and you can do this kind of many different variations of that. They are all corollary of that. And then you get if I want A itself, like polarization, then what do I get? If I say my A couples to electric field, and I want to know the polarization, which is like solution dynamics, then what do I get? I get polarization relation function. And that's the one kind of things Runjit and all these people calculated. And that is your response. And that is what we calculate. We measure experimentally solution dynamics and all these things. Because once you know the delta P energy is trivial, right? E naught delta P is the solution energy. All right. So we know all these things now. So then basic flowchart is the following. I start with the Liouville equation, and then I do the perturbation. H naught H prime. As a result, my phase space distribution gets perturbed. Then I write the Liouville equation for full density matrix. I generalize the Liouville equation and find a formal solution of the first order differential equation. I find the response that goes over to time correlation function. This is the flowchart of the linear response theory. So fluctuation dissipation theory follows from these things, and that I'll do in a minute, in a little later. But I rather want to do fluctuation dissipation theorem through 1/6 perturbation, 1/6 positional technique. So let me do now, show you little fun. If I can get the fun part going, let me see. Now, he taught me how to do it, but it is not working. My student taught me, Ved, are you there? Why it is not coming?
So we are still seeing the PDF, sir.
I understand that. Let me just stop share and see if I can get. How do I get that? How do I get that? Okay, I go back, I share screen, and if I'm lucky, I am lucky. Can you see now?
Yes, we can see the doc file.
Whatever it is, but something is there. Now you can see the equations.
Yes, derivation of Stokes relation. Yes.
Wow. Now this is a beautiful two one-line derivation that I have done myself, and I'm very proud of that in the process of it. Okay, Stokes relation. I told you what is Stokes relation. Velocity equal to 1 over friction into force. As I claim, that is the mother of, that's the beginning of linear response. So I start with the one I just derived, equation 11. and this is a time correlation function. I say h equal to h naught h prime t. Just I showed you the perturbation. Now I am pulling a particle with a force. The particle was the h prime is time dependent. At time x not equal to 0, particle was at origin. I pulling with a force F. So my energy, additional energy is h prime is fxt, force time the displacement, right? Work done. Correct? Okay. Now in the place of the conjugate observed is, so now I put back in my average perturbation. So my Vx is my B. So put that, so it's B A dot. So velocity that I generate is the perturbation, right? And then that is this quantity. Remember there's the beta. I put the beta there, 1 over kBt. So Vx is B A dot x dot F. Now I get in the long time, take the long time limit. This is Vxt is 0, Vst, this V0, F by kBt. Okay. Now we can generalize the equation as is F by kBt, Vs, V0. This is nothing but diffusion. So my F by F, remember F is external force here, by d by kBt. D by kBt is zeta. So I get Stokes law. So from Kubo's linear response theory, I derived Stokes law. I took a walk 100 years back. Okay. But this is the beginning of that. But so I can derive now Stokes law from, and it's nothing new, but wonderful application of linear response theory. That where linear response theory started, I needed to go back there, right? Like going to Gangotri. So pretty pleased with this. Now I'll show you my one-line derivation of Kirkwood formula. This is actually every time if I ask you some question or other. No, I derive Kirkwood formula from linear response theory. Now d equal to Vt V0. Okay, now I have derived, this is not linear response, Stokes relation. From Stokes relation, I know V equal to 1 over F, but still there are some nice steps are there. I put it that, actually that also tells you why Kirkwood's formula has limitations, because it's an average kind of coarse grain description. I put it there, I get 1 over 3z square equal to Fs. I take it on the, remember the factor of 3 is very important everywhere. Dz square. Now I right now keep one dz and other thing like kBt by d. Dd gets cancelled. So z become, oh, this is your Kirkwood's formula. So if I use, which we do in StatMat, Stokes law is a fluctuating thing, and I'll probably have a little bit of to tell that. Then I get the Stokes Kirkwood relation, Kirkwood derivation, Kirkwood expression, which is always very difficult to derive from Stokes law. And as I mentioned that whatever the prefactor in this equation is the response function, and that is the time function representation. Okay, so these are the two derivations. One is the Stokes law from linear response theory. And now I'll go back to do little bit. If I can find my file, I'll do the positional technique. Okay, now let me see if I can make it bigger, because this is a lot of fun. No, it's not getting bigger. It's a 100%. Why it's not going more than 100%? I don't know. Okay. So positional technique, let me give a brief that it is. So what we did, we used the time correlation function. We derived many expressions for time, not many expressions. We derived many places where time correlation function is important. And we discussed it. We discussed linear response theory, which is Kubo's linear response theory. And then I'm going to do fluctuation dissipation theorem, but I'll do Bala's one. So now the question arises, okay, Well and good. You told us about time correlation function, that how useful time correlation function is through linear response theory that explains the world, at least the linear world. And that is the thing students all do, but they do not know that where these equations come from, that why we calculate energy time correlation function for solution dynamics. The detailed derivation part should be done. Now, well and good. So now how to calculate the time correlation functions? That's the next thing. So I'll now tell you how to calculate the time correlation function in the position of a technique. In the process, I'll do linear response together. So this was done by Zwanzig in 1960s, early 60s. And so what Zwanzig did is a very clever thing, which again, Zwanzig gives credit in his one of his articles, I think the master equation article, because he wrote 2-3 articles only on this, to von Neumann. Von Neumann was visiting National Bureau of Standard, and he gave some talks, and once he caught up that he said that the eigenfunctions of Liouville operator can serve as a basis set. Now, I have really studied this pretty well. That's from Sturm-Liouville operator. This part of it. I have not been able to convince or find anywhere that it defines a complete basis set. That is, complete basis set means you don't need to do anything outside. But the way once it used is actually that. Okay. So, but I now go through quickly. Again, it's a fairly trivial derivation, but you have to practice it many times because it's just like India response course. It is. So again, we start with Liouville equation. So what happened now is this figure. Everybody can see the figure, now.
Yes, sir.
Okay. So basic idea is the following. It comes from hydrodynamics. So we have a space. We have a bunch of slow variables whom we want to describe, and we know equation for those slow variables. But we know also that they don't form a complete set. Like nothing tells me Liouville equation. They are conserved variables, big deal. So they are slow, big deal. But nothing more than that. That does not mean I can describe a phenomena which is coupled to these things by only those 5 things. Okay. So then the idea was that how do we include the next set of things? How do I write an equation of motion of an arbitrary quantity P by projection on A? And this A can be a set of slow variables which can be hydrodynamic modes, but it can also be, I can augment that by product of them, the next set of slow variables. It looks a little formal, but it's actually not very difficult to do this. For example, let's say I want to get the velocity of a takt particle v, and I write velocity time correlation function, because as we are saying, we are calculating velocity correlation function now. We have gone to the next level, v0 vt. I now write v0 vt in angular bracket, v0, then vt is e to the power ilt vt. Now I know my Liouville operator that couples will work on a mode that couples to my velocity, takt particle velocity. What are they? One are the current modes, because these current modes of the liquid carries the particle velocity. So I have the current modes, and I also have the density, because the cage density can relax. Now I find out by symmetry of the time correlation function which couples to my modes. So once you start thinking like that, it's not that difficult. You can do some amount of advance. Okay. So we are projecting, we are interested in B. We know about A. We are projecting on A. Okay. Like if you're solvation dynamics, then B is the energy and A could be the polarization. Remember there's two very nice papers. Only one paper is okay. Denny and David Reichman they did this. Denny was on phone with Sarika a lot. Those days we were doing these things. And they did that. Raman, third order Raman response, very famous paper of Denny and Reichman. And there they showed that if you write the third order response, that is polarizable time correlation function. And then polarizable interaction part is the Austen tensor, which they can decompose, express in terms of density. So they then wrote the pi, the capital pi, which is the polarizable tensor, project on the density mode. And they derived the mode coupling theory equation. Okay. So right now I'm going to go with the level equation. So AT, remember, AT is e to the power IL A. AQ when has no time dependence. The t equal to 0, sorry. And I take the derivative, I get e to the power ILT, LT. Then I do something, actually, Zwanzig did, the identity that I project on that. So P plus Q is 1 because it is just projection and orthogonal, two together becomes the 1 because you can decompose any quantity into two perpendicular, one along the A, other the orthogonal to that. So P plus Q is equal to 1. So you put the P plus Q there because ILAQ. This has many people have done it many times, and then you get two terms. Okay. Then again, just like before, you are going to work on them. You say e to the IPL, ILAQT, then that becomes A dot. And I projected on LA, so ILA, that will become A dot, remember. And then I write the definition of the position operator, which is the definition of the position operator in the figure. And then I get e to the power ILTP, ILA. I can show that it's just A dot, and A dot is a frequency, and that is omega. That is defined as omega. So EIL to PILT, important thing to know about this quantity is that everything is in the what we call our own subspace, is the A that we know. So that defines a frequency. This is defined of the frequency term. Okay. Then I'm sorry, this is really very small. This is the same thing going on in the matrix manipulation. Okay. Now, one can, so since this equation 12.7 is very bad, I'm not going to go through details, but one can do by manipulation of the very similar kind we have done in the linear response. You can derive an equation which is, I'll go back, don't worry, I'll go back. I go on to show you the equation. The equation of motion of A is then I omega t AQT. The other two terms I am showing. This is the first term. Remember, we had two terms. One of them e to the power ILT, ILAT. E to the power ILT, P, e to the power ILT, P, ILAT. That becomes this omega Q term. Then another term remains that I'm going to work on it a little later. But though that term becomes this this equation, where one is a random force term, which will only have Q, capital Q, which is the orthogonal subspace. And here, gamma is the orthogonal subspace, A is my own space. So now, by doing that, main quantity is that this gamma T, gamma QT is a force time correlation function that I'll discuss in a minute. So this is the Langevin equation, because this is the friction, this is the random force. So friction and random force are connected. This is the second fluctuation theorem of Kubo, which is through Langevin dynamics. So Zwanzig derived it formally by saying what is my friction? How is the friction exactly defined? Friction is exactly defined in terms of forces which are in the orthogonal direction. So let us do, if I can do this little bit in the small thing. Okay, first term. So we have two terms here. First term we have done is simple. Second term, it is our ILTQ, ILAQT. That's the thing we are going to do now. For that, one uses a matrix identity. Actually, one can do it many different ways. You know, best actually is do a Dyson expansion, where you have 1 over m plus n. That is, you write one same as 1 over m plus 1 over m n 1 over m. Okay, so that's the first term of the Dyson expansion. So I go again, I Fourier transform this, Laplace transform this thing. I can write 1 over m plus n, get 1 over m plus 1 over m n 1 over m plus n. That's exact. Dyson expansion means the next last term 1 over m plus n is again 1 over m. Then plus again 1 over m n 1 over m n 1 over m. I'm saying all these things so much because Dyson expansion plays a very important role in non-equivalent statistical mechanics. So the same thing we are doing, but we are not doing the expansion yet. Okay. Now we have this 12.7. So 12.7, I now write m plus n is my p. I write as p and q. So m is minus il, n by IPL. Then I put it there. It will be ILT e to the power ILQT d tau e to the power I. It is so small I cannot see myself. L t minus TPL. Okay, so m by IL, n by IPL. Yeah, if I make that identification, that this quantity is general, it's an identity. Okay, all I have done the m by IL, n by IPL. Then I get that equation. Okay, 12.8, which is exact, and then I take the derivative now. First term remains. The second term, I have now taken the derivative of EILT. Yeah, you're getting a little confusing. It's exact. Do it yourself. You'll be able to do it. I would have done it a little differently if I have done it myself. Again, I did do it myself. So e to the power IQLT. I take the derivative dA dt. That is have e to the power ILT. First term is that. Then second term is second term is this term e to the power IQLT QLT. So I again write e to the power ILT here. I write again. I put e to the power ILT again. That identity e to the power ILT. And when you do that, you get 12.9. And then the important thing is that this term, the equation 12.9 and equation 12.10, FQT, the next last term, that is e to the power IQQLT. Just a minute. So now this Q, there is only Q here, left and right. I have only Q acting. LA I cannot touch. So this Q, I can put a Q in front of it because that acts on the, it just projects Q on Q because that is equal to 1. And then I can get this quantity. If you were IQLT is an interesting quantity because it is propagating in the orthogonal space. So A dot is formed here. Then A dot is multiplied by Q. So you project in the orthogonal space. Then you further propagate in the orthogonal space. So that is the reason F is the completely in the orthogonal. It is nothing of our subspace A. And I should have probably clarified it a little bit. Okay, and then IPLFT again. This is a bit confusing. IPLFT, I again write F. The definition of F is QF. So this definition I put in here, QF. And then P is 1 minus Q. So I is 1 minus Q. Then I now going to evaluate this quantity P IL FQT. Now FQT is this quantity PILFQT. PILFQT is, all right, I'm getting confused here myself. This always happen position order technique. Okay, so but let's try it. So 1 minus Q, so ILFQT. So I take out the LQ FQT, so LQ FQT here, and then I have whatever it is, just it is correct, but I cannot seem to get handle of all the terms here. It is possible. So I think I'll leave it at that. If I can come back later and do it. So whatever it is, its end result is quite simple, that you get the decomposition, and that goes over to the time correlation function again. These omega QC QT. This is much better doing in board really. When you're doing in board, you never get problem because you are deriving there. In online, this is always a problem. Looking into this kind of a gets complicated. Okay, so basic idea. Then I carry on. Probably one day we'll do position about a technique itself, and that should be done not like this. So this equation, which is an exact equation, irrespective of the derivation, which is giving here, there is a possibility that the derivation is a little bit screwed up. Now, this 12.14 is the exact equation of A in terms of the dynamics in its own space, which is I omega Q, dynamics in the orthogonal space, which is the second term in the Langevin equation, it is the Langevin equation, and the force is the dissipation equation. So this is the nonlinear Langevin equation, people call it. This is also called the relaxation equation. And this can then be trivially transformed by multiplied by A minus Q, and you get this equation of the time correlation function. As I was saying, that this is the this equation. I don't want to put you off, but this equation is the starting point of all studies of statistical mechanics, analytical studies of statistical mechanics. This is called relaxation equation. So right now, let me comment on that this quantity I omega Q can be calculated easily. If you have only one variable, then I omega Q, then this omega Q, if you use one variable, then omega Q is 0. That because LA is A dot will be 0, but it will be non-zero only when you have A as multiple variables. Because A is we are doing as a vector. Like A is V, X and V, then this term that V and X dot V, that will become non-zero. So if you have, that's why in ordinary Langevin equation, you have, in the absence of a force field, you don't have this first term, you only have the second term. When you have a force field, then that systematic term comes with the frequency, omega Q. So that is the Langevin equation that is the Langevin equation in the harmonic oscillator force field that we use in chemical reaction dynamics to calculate the rate. But in ordinary Langevin equation, when you calculate the inflation diffusion, then A is the velocity, and then you have this Langevin equation derivation. So this is the exact derivation of Langevin equation formally. Still, it has no Hamiltonian structure. And this derivation, I think, is a little bit taken from my own notes. And this is a little cumbersome. So I have to clean it up, but basic philosophy remains the same. Basic philosophy is that I want a variable B, I project on A in order to get that. And then, so what are the two steps involved? I need an equation of A, and A itself is a system of variables. And then this procedure leads me to an equation of A. It's a rather elaborate procedure, but exact procedure to derive an equation of motion for this variable A in terms of which are within the A and which is orthogonal to A. So I don't want to confuse you anymore because it's getting it's a difficult subject and it's getting a little bit confusing here. So there's no point of making it more painful. But this is the equation which is derived. Now, when you do fluctuation dissipation theorem, there is the fluctuation and dissipation who are connected. That you can go through Kubo's linear response, but that's not really anything more than linear response itself. Okay, like one can get the susceptibility, and then you can say susceptibility connected to fluctuation. Or connected to time correlation function, and time correlation function is of a fluctuating quantity, but that itself is not a very satisfactory. It's kind of go around of the fluctuation dissipation theory. But this is the exact statement of the fluctuation dissipation theorem that comes from the from positional technique. Okay, so this is I'll send the notebook to A. It is going round and round and round, but it is exact. You know, up to 12.5 no problem, 12.6 no problem. Now 12.7 no problem. Now 12.8 you decompose. This is what I remembered. My confusion is that I remembered that I do M and L by P and Q. That is so it's possible that here these things are a little bit unnecessarily complicated. So I have to clear it up, and I'll probably send a derivation to Shumon, and Shumon will add that to the lecture notes. And I'll send this also. So I just want to have one quick how beautiful this projection operator technique is. One application that will make it little easier for you. Okay. So this is the velocity time correlation function that I was talking. ZT is, just take one of the components, UU. And then what you are going to do, this e to the power ILT, I'm going to project e to the power ILT, which is the propagator, e to the power ILT into my degrees of freedom. So I write ELT into P into EILT. I have not yet given P yet. What is the P? Now I have to choose what could be the P. What are the modes? My velocity will be, velocity of attack particle will be connected. As I was already telling, there are two modes. One is the current and the density. Now, if I put, look here, if I put just density, then density will be, if you evaluate that, it will be 0. If you put current, if you evaluate it will be 0. So next is the binary product. That's why you hear the term binary product. You put the binary product, and now you put that binary product. Now again, a kind of intricate algebra, but this thing is somewhat simpler. I now calculate this e to the power ILT, this P, which I have put here. So my P goes in before ILT and after e to the power ILT. and my P is projecting on rho k j minus k. That's my the A that we projected on over there is that quantity. And so PB is just the definition of positional operator technique. That this is my projecting B on A. So this is that figure I showed. This is my A. The one is -1. This quantity called vertex. Then my A. This is my A because I'm projecting B on A. And what happened now? This can be evaluated. This quantity can be evaluated not too difficult way. Like here, if I can do the, we realize one thing that I put e to the power ILPT, then this is the quantity I have to evaluate. And this goes, this and these brackets are nothing but it goes to the denominator. I can evaluate this quantity. I can evaluate this quantity, and this is done here. That P to the power ILTP is this. Then what happened? This you decompose rho k, and you get these kind of quantities. You know, this is the famous decomposition theorem. You have this time correlation function rho k j minus k, and that there are 4 dynamical variables. You separate 2 and 2. When you do that, you get 2 time correlation function. One is density, and the current. And then the final expression is very simple. So you get an expression for the velocity time correlation function in terms of this self-dynamic structure factor and longitudinal current and the transverse current. These are not really very difficult. If you work out step by step, everything works out beautifully. Like, for example, take this quantity. If you want to do that, then you will note that here is jk, and what is j? It is sum over vi and the velocity of the particles. Sum over that, and then position delta r minus r. So these quantities then and to I and j comes, and velocities of I and j don't. They are not correlated. 2 different particles velocity not correlated. So it becomes vi square. That becomes, so this is the kind of things 12.27 equation has been done. That rho k jk, if you evaluate that now, the way I am saying, writing jk, then you will find that this is just one of them is 1 over n, and there is delta alpha xx. So this fairly formidable thing is very simple. Like here I was saying rho k j minus k. That's what I'm saying. If you do these things, then I and j velocities are uncorrelated, and vi squared, then you have kVt by m. Similarly, this quantity also become kVt by m delta. So all of these things are fairly easily doable, and everything. And then when you do this one, for example, on that, e to the power ILT makes these 2 quantities time dependent. Rho k become time dependent, j minus k become time dependent. Once they become time dependent, I have rho k jk at time t equal to 0, rho k jk at time equal to t. So then I do this is called Gaussian approximation. I separate the rho k into jk, and this is this thing. So then my time correlation function, after doing all these things, is fairly simple, 12.29. And then you just transform it into the sum into an integral, and this is the expression that comes. That goes over to, this is one of the expression that goes over to Stokes-Einstein. This is one of the Stokes-Einstein relation. Okay, so this probably is a very good example to study the velocity time correlation function and the derivation of Stokes-Einstein relation from this by using the position operator technique. So this it is fairly straightforward. It is doable, and no ambiguity. This is actually simpler thing. The position operator technique, I would recommend that you go through this. This is also not difficult. but there are a lot of these tiny little steps there, and a lot of manipulations. Like once you are writing P you are writing as P plus Q. And for example, here what one is doing is 11. I'm coming back just to that. You're saying that what kind of trick you use. F is orthogonal space. It has only Q. So I am entitled to put a Q in front of it. So I put a Q in because F is QF equal to Q. Some of the properties of position over technique that I should have done, they are idempotent. Okay. And that P square equal to P, Q square equal to Q, and QF equal to Q because F is already in orthogonal space. So QF become, I can put it there. Then I write P equal to 1 minus F. So then I separate it out because of the 1 and Q. So Q, IL, QF is only in Q space. So that is then the P that is depending on PI level case. Again, I have to, so L, propagation of L on F introduces both Q and my relevant subspace. Again, I have to separate it out. So that is the game that goes on here. Everywhere you have to separate out the orthogonal space and the system's subspace. And at the doing of all that, you can show that this quantity, that this equation 12.9, which comes from equation 12.8, which comes from equation 12.7. 12.7 goes to equation 12.8. 12.8 is rewritten as 12.9. And then in 12.9, you look into the character of the two terms, and you can find that the middle term has only Q, because L has both L and Q, but then you project it on Q, and then you have already separated out that by matrix, that thing e to the IQ. So this is becomes a random force term. Then important thing is to show in 12.9 third term. So first term is the frequency term. This is the random force term, which is orthogonal subspace. Then this one I have to show that this is nothing but time correlation of this quantity, integral over time correlation of this quantity. So then I have to show that this quantity IPL, IQLT, QILQT is F0 FT. Okay. Why the angular bracket coming? Angular bracket coming because P has an angular bracket position of it. And that is done in this step. Okay. This step 12.11 and 12.12, those things has been done. Where shown that this quantity, remember QIL is F. So that quantity then goes over to this, this quantity goes over to this quantity, which is the random force term. Integral of that is then the friction. So that is lead to this thing. So it is not really difficult, but you have to systematically from 2.7 go to 12.8, then you get to 12.9, then you immediately first and second terms are easy. Only difficulty is the third term, and you show the third term is the time correlation function of the second term. That's the fluctuation distribution theory, and that can be done without it. If you you should do it yourself by the pen and paper. If you're on a board, that is the difficulty of not having a blackboard, because when you do the blackboard, you are doing in your hand, and that's what we are used to. Okay. So this is done. So this is what I wanted to do. Position over technique. Yes, with some hiccups. Actually, I believe that I've been able to tell that what is the. Let me go back to my slides to finish. So this again, stop. Then go and share screen. I hope I'll get my slides. No need to be on step. Okay. So the so Kubo's linear response theory I've done. I've derived Stokes law. I told you the online derivation of Cartwood formula, and the interesting thing is that much of linear response theory you do the fluctuation. So there you assume that the relation between velocity and force, which is a macroscopic relation, goes over to the microscopic relation. And that is the very essence of the Onsager's regression hypothesis. Just a minute. But why is this? I cannot make it larger. This is funny. Why it is not becoming? Why I am not being able to go to the A mode?
Full screen mode.
Yeah, no, whole thing. It is this. Your screen sharing, okay. And what I'm saying, I'm not getting the PPT sign, so which is allow me to do Baba. Okay. So Onsager reciprocal relation. This is the last thing that I'll do. And so what is then Onsager reciprocal relation? You have two forces. J is a vector, X is a force, which is a vector, L is a tensor with the matrix. So that means that's written below, J equal to Lik xk, and the Onsager reciprocal relation proves that Lij equal to Lgi. These proofs is a very elegantly done by Landau-Lipschitz. It is not the one that Onsager did is something is a little bit more complicated to understand. But the way Landau-Lipschitz, this is the one who everybody uses, and that's a beautiful so let me, if I not, then I'll just, but if I find it, it's fine. If I can find that part of my note. Okay, now I want equilibrium step, man, position operated technique. Then I want, this is in download. Okay. I want, I am a bit sorry because I made a PDF file of all of them. What knows where the PDF file went? There are too many equations. Okay, this is not it. Okay, now can you see this or you cannot see this?
No, sir, we cannot see the doc file.
Okay, just a minute. Now?
Yes, we can see now.
Okay, so this is a beautiful proof, and I'll just briefly go through that. The Onsager's reciprocal relation. In my mind, these days it's better done after. Okay, so Onsager's reciprocal relation, and this is the relation. I said J is a vector, and let us consider two dynamical variables, A led to by 2 matrix. Okay, the way proof goes is very nice and very, very simple. That you start, and it's a complete use of time correlation function. I almost certain, though I'm not sure, that means that is, I don't know, but I would guess the Landau with this. Okay, so xi t plus tau xj t xi x3. This the first equation there is just the definition of time derivative. Okay, now xi t plus t x3 minus the 1 over tau. So I have xi dot t xi t. You can see that's all equations written by me. So you know, if my equations, you see, has to be dot has to be somehow bit bigger. I don't know how, but I have to take students help to do it. Okay. now I use the two properties of time correlation function I already discussed. One is that time translation, and next is the I do that xit plus xj tau, so I can minus t minus tau. Did I make another mistake here? Let me see. Okay, xit plus tau, and then xgt plus tau. That last equation is time translation. Time translation. Okay. Now, and okay, so I'm sorry. This is not tau. This is t. On the first thing is just t here. Okay, that's why I got confused. So if it is t, then I can. It doesn't make, since that t, it can be on the right hand side, it can be on the left side, right? Time translation. So this is t minus tau. That's correct. Then that is same by, this is time inversion and this is time translation. Okay, I can add plus tau to both of them, then I get this t plus tau. So I use both the two properties of time correlation function that I discussed. One is time translation and it is time inversion, parity actually. So I have already discussed this. So if this quantity xj t plus tau, xi t plus tau, xj, then I can write that as xi t plus tau, x t minus this thing, and then that I get xi t, xj dot t. I have shown these two are same. This one and this one I have shown is the same. So then this quantity xi dot xjt is lik xk xjt. So I can then get, now I can show separately xk xjt is lij. No, sorry, xk xj is delta kj. So if it is delta kj, then it is becomes lij. Okay. Remember, these are all same time. So there's a time missing here. This is same time. This is the same time. At the same time, this is a Kronecker delta. That is given here. It's a Kronecker delta. Okay. Now I can go and do this xi dot xjt. I do xj dot xit. Then I can do the same thing, and I get LJI using the same Kronecker delta. Now I have shown that before by time correlation, these two are the same. So then that means that Lij equal to LJI. So that is now proved that this is the simplest possible proof of the Onsager reciprocal relation through time correlation function. Of course, Onsager didn't do it through time correlation function, okay? Because time correlation function became so popular later. I forgot how Onsager did it. And I meant to look it up, but I did not. I was more busy writing this derivation from Landau. Okay. Now, however, what we have not discussed is that these xk xj, capital X, remember? So in what I have done, this is the Onsager's relation, J equal to L dot X. And so J is the force, and sorry, J is the flux, and X is the force. What I have done here, following Landau notation, that J has been replaced by X dot. You know, that small x, not capital X. Capital X remains the force. Flux is given by small x, you know, in this notation. So the Onsager's reciprocal relation remains the same. So why Landau did not use in notation J? Because to him x is the force, and that force is conjugate to small x. That means x is like in my Stokes law, x is the capital F and v is the velocity. That's exactly same thing, and L is the 1 over friction. It is the same thing, except in Landau Landau-Lipschitz version of Onsager reciprocal relation, your everything just small x and capital X. Capital X remains the force. Small x is the one that is driven by capital X. Well, fair enough, you know. And so this is the derivation, which is very neat. But in that derivation, as I told you, what remains incomplete is to show that capital X and small x at the same time are Kronecker delta. And that itself is a long proof that we can do without for the time being. That is given here. At the same time, they're Kronecker delta, equilibrium averaging. And that requires use of entropy fluctuation formula and all other things that I'm not going to discuss here. So this is the Onsager reciprocal relation. So why Onsager reciprocal relation is so important? Let me get back to. I hope I'll be able to go to non-equilibrium stat mag. Okay. Why is but bothering me? I cannot make it a full screen. Well, that means the projection mode. Why I cannot make it a projection mode? Zoom has still either lot to. You are screen sharing, correct? I'm screen sharing. Okay, and I can stop screen sharing, and I can go to share screen, and I can do this. No, it's again the same thing. It's not coming. Okay, but I have to work with this now. So basically, why Onsager reciprocal relations, and what is the connection with Kubo's linear response? That what Onsager assumed, what A brought out very nice, Landau brought out very nicely, that it is that remember the time correlation function that I have done is the fluctuations. So basic idea then is that the fluctuations or time correlation function of the fluctuation obey the macroscopic law. That is the Onsager's regression hypothesis, that I perturb a system like we did in linear response or any other thing. The system relaxing back to the equilibrium. This relaxation is same as the relaxation of the fluctuations. This is actually paramount importance, that the fluctuation, that the macroscopic fluctuation obeys microscopic law, or other way around, I can say that I assume that the microscopic fluctuations can describe macroscopic relaxation. This is what we always assume in our many experiments, solvation like that. And everywhere you have a perturbation, and then we say, well, it is a 1990 time correlation function. That is nothing but Onsager's regression hypothesis, and also called. So that Onsager's regression hypothesis becomes the same as the linear response, or rather, Onsager's regression hypothesis gets the Onsager's regression hypothesis gets its justification from the linear response theory. So you need to think a little bit about it. It's, as I was saying in the beginning, that the synthetic view, that all these things are the same. That Onsager's reciprocal relations, which through time correlation function formation, derivation is a neat and clean, and you have to do the derivation. But the basic philosophy of Onsager's reciprocal relation is the same as Kubo's linear response. And that is actually Landau's beautiful derivation does, that it shows how it is the time coordination for motion. Onsager reciprocal, which is so formidable theory. And why, what I have not been able to do, and I would like to do, to derive this relation through a perturbation. That means I put a electric field and a current flows, and but a thermal gradient sets up. So the flux in heat, because of a force in current, that is why L is a matrix. That is interrelationship, that the electric current can generate a heat, and heat can generate electric current. That we know, Seebeck effect and Peltier effect. But the proportionality, linear proportionality, L1 to L2, that nobody thought. Onsager was given Nobel Prize not just because he proved L1 to L2, but he, in the process, he introduced regression hypothesis, which is, I said, the same as linear response theory. That's why Cooper never got the Nobel Prize, because it was always told that Kubo's linear response theory was already in Onsager's regression hypothesis, which is fair enough. Though Kubo did a huge service by systematizing everything. So this Onsager's regression, linear response, Stokes law, Einstein's Brownian motion, these are all very connected to each other. All of them require you to calculate time collision function. That is the catch. So the time correlation function is done rigorously through position operator technique, which I think I have now, my second iteration, I hope I have been able to explain a little bit better the derivation of the equation. So the relaxation equation is the exact equation for time correlation function, which students certainly should study that relaxation equation, because it is like you go to a place, you are going to Gangotri or somewhere, and you go to one intermediate place from where all roads flow. But ultimately, you have to go to this, and so that's why Zwanzig's position order technique plays such an important role. It tells you how to calculate the time correlation function exactly, and that has been done. This Zwanzig's position order technique has been used to essentially the relaxation equation of Zwanzig is the starting point of mode coupling of many other applications, but they are all completely dependent on or started from Onsager and Kubo. I think I have nothing else probably to say. Yeah, so I think this is it. This is it. I think this is a fairly heavy thing, and I should have cleaned up probably the derivation of the position order technique, but on second iteration, I think it's fairly simple. I should have created a flowchart. I think I'll create a flowchart for my book, because the flowchart will go backward. Flowchart will say, okay, our purpose is to introduce the fourth term first. That is the orthogonal particle wave. I think one should give the student the motivation that why you are doing it before you do it. That's what everywhere I've tried to do with the flowchart, and that is, I think, missing in the position of a technique. Okay, dokie. Rajiv.
Okay, sir.
I think
Yeah.
it's done.
Thank you, sir. So the floor is open for discussion. If you have any questions and queries, please ask. I can see one comment in the chat box, which Nilanjanadi asked you to elaborate on the flow chart long back around 416. Maybe you were showing some flow chart that she wanted you to elaborate.
Oh, you did not see the flow chart.
Yeah, unfortunately, my
not you. I have to. I comment I made to this flow chart.
Yes, this I actually dropped out for some time because my connection went bad. This I got in your text, Professor Bagchi. You also mentioned some kind of a, how to get to the time correlation function from the exact response that one is seeking. I think you were saying something like that. And
No, I think what are the, this is the first one, flowchart, and these are other flowchart. I have not done a prediction operator technique flowchart that I should do, so that these derivations become kind of clumsy that it happened today. It should not be. It's actually very clear derivation, an exact derivation. Yeah. So I say again, you can guess. So no, guess part comes from projection operator technique. That's okay. I understand what we mean by guess. See, guess. What I meant is the following. In Stokes Law. See, whenever people talk of Stokes Law, people go to Stokes Einstein, which is actually a mistake. Because that's theta equal to 6 pi or 4 pi eta is a much more trivial consequence. More important consequence, the velocity is 1 over friction force. That's the beginning of in my mind, beginning of this linear response theory. That's also both Kubo and Einstein. That is the beginning of everything. Somehow that is not giving proper importance. Maybe I think we chemistry students, we don't want to tell them the Stokes Law, which is a phenomenological law. But I showed you that you can derive it from linear response. By guess, I meant what is the following thing. That let us see, I have velocity, a prefactor, and then force. Then I know that my prefactor should be in terms of the force type correlation function. For example, Navier-Stokes equation, what do you do? G dot, my current, comes as a minus viscosity into dvx dy plus dvy dx, that kind of term, right? Then you know that the viscosity will be given by current type function. So everywhere, you know from, you don't know the exact form, but you know what is the time correlation function. Okay, let me tell you a little bit in simpler. I know specific heat equal to energy by heat by time. Then I would know that my specific heat will be given quantity, which will be fluctuations of the energy. And that exactly becomes like, so you say you are doing a very, or do you write the Hamiltonian, the perturbation? Perturbation, you know, electric field, that creates polarization. What is the measure of the polarization? Is the dielectric constant. You then know that your dielectric constant will be polarization correlation function. That is the thing I'm saying you can guess. So if you are doing a new experimental theory of a new experiment, if you can put it in terms of the response which you are measuring and the perturbation, if you can write a phenomenological equation for that, like we do in dielectric constant, electrostatics or dielectric relaxation. If I know the phenomenological equation, then what I'm telling, I know the time correlation function for motion. I can then guess that what is the time correlation function? What is the relevant fluctuation? What is the time correlation function? Actually, Stokes Law is a wonderful in that, because Stokes Law and Could formula, all these things are really very nice, because I have a V equal to 1 over ZAF, and that is a macroscopic quantity. Then I say, okay, I assume it valid for microscopic quantity, so that I have on a particle, I have a fluctuation in force. And as there's a fluctuation in force, that will give rise you have velocity, and so the friction is given by this fluctuating force time position function. That exactly is actually exact version of Kirkwood. I didn't go into the detail. That's not the total force, it is the fluctuation force that goes into, and that's the whole problem, because calculating the fluctuating force, and that again exactly done by John's expositional technique. And that my talk file is so hopeless that I got depressed just looking to them. They should have been so much nicely done, but when I try to transform those things in PPT by copying and cutting, it just too much of work. Every equation by equation you have to do. Old days, many of my students used to do that, and I now realize how much work that they must have done in the form of Shankar particularly. This is what, there's a beautiful thing is there, in the level of the time dependence. There's so much correlation, so much connectivity across non-equilibrium stat mech. That connectivity is not really taught because it's probably difficult, but everything is connected here. Kirkwood formulas, John's positional technique, Stokes law, they are all same basket, so long you know how to. And what is essentially holding them together is the linear response theory and also its regression hypothesis.
Okay, sir, I don't see any other questions in the chat box. Anyone would like to ask any questions or comments? Please raise your hand or unmute yourself and please go ahead. So as usual, we will be uploading the recorded version of today's session on the
Rajiv, I think somehow somebody has to do I think the projection of a technique part, I think the slides should be put in that derivation, but it won't be possible for me to type those equations. I can type in math type, but PPT is a lot more work. But maybe I'll try the PPT version, or I'll ask somebody to ask. You say that part will be replaced.
okay.
Because it will take me quite some time to do into. I did not. Before, I have always taught question over technique many times, but I have always taught with the blackboard. And blackboard, it is so easy because you write this either Dyson expansion version or e to the power ILT on the right side. And then you write P plus Q equal to 1. Then you write this Q. So you write down on the right side all the conditions, or what you'll need on the right side of the black. Then it's a trivial exercise to go through the derivation. Here, this online, that's a real difficulty. That it is a particularly the doc file, so little, I cannot myself see these equations too well. Because those equations have also not been my I think it was written by one of my ex-postdoc from our notes. The notes were old notes. So that has to be those equations must be made even doc file much bigger. Because I like the equations very big, even in doc file, and we put them in the box. But that is the main thing that one has to. That's why teaching in a blackboard is so much better, because you know what you are doing, and you have the equations on the blackboard, and there is a great relation between your hand and your thinking, because because we are used to hand plays a very, at least in my case, very important role in my thinking of equations. If I cannot write the equation myself, it's just very difficult for me to I feel very jittery and very uncomfortable. And that I think is the difficulty of these kind of equations. But I think basic idea is this: the basic top things on this time-dependent statistical mechanics course that I think I have done repeatedly. That the linear response, Onsager's regression hypothesis, Stokes law, Einstein, these things I have said again and again, and these are the basic ingredients to think about this field. And if one can think about it, like one giving a talk, I have heard people talk of solution dynamics. People talk, they never say that if a faculty candidate comes and tells us that this quantity is energy that you are measuring, yes, it's a big shift in energy, big perturbation, we are changing 200 centimeter inverse, and we are assuming that this linear response, so we can talk in terms of dielectric constant or dielectric relaxation. Anybody says that, that will be tremendous impact. Even in lecture, people immediately will laugh that guy. I remember this guy Join went to Bombay. He was talking of Marcus theory. He said a few lines like this, and we are really laughed him. He was immediately taken, given that offer. Because we realized that guy trying to understand. Like Marcus, again and again, Marcus said that electron transfer is the way Marcus took tremendous pain. Marcus himself later told me, Biman, I took so much pain in establishing that the non-equilibrium polarization is why it is relevant in electron transfer. That was his whole paper of 1956. Lot of that in non-equilibrium polarization. Later it was Alberi who just showed it's just nothing but two harmonic oscillators. They're interacting, and you find out the barrier from that. And you take the frequency of the two harmonic oscillators the same, then you get the barrier, which is exactly Marcus equation. And so it is nothing but response. That means your harmonic oscillator frequencies are fluctuations of correlation. So your linear electron transfer reaction is a statement of linear response theory. So these are beautiful stuff, but it's not taught like that. It should be taught like that. Okie dokie.
I think, sir, we can surely, work with you and then upload that PDF version of the note about this projection operator technique along with this recorded version of.
No, position operator technique is fine. What I have to send you the PDF file, but I have to at least make those equations larger, then make it PDF, and maybe add a flow chart, and then I'll send it.
Sure. Yeah. Okay. Okay, sir. Thank you, sir.
Okay,
so,
then.
I think with that we are done with today's session, and we are done with this as of we have already told that in the beginning. This is the last lecture in this series by Professor Bagchi, and our next lecture in this platform will be given by Professor Arnav Mukherjee sometimes in September. So we will come up with the exact announcement of that talk in due course.